Bueno, pues buenos días a todos. Muchas gracias por venir y asistir a este pequeño, esta acogida por los nuevos entrantes. Y bueno, pues como ya sabéis, eso va a ser una media jornada donde los 4 últimos incorporados nos van a dar una pequeña presentación. Y bueno, el primero speaker de hoy va a ser Pablo Fonfría. Entonces, well, I will switch to English now for everybody. So, José Pablo Fonfría did his PhD in the Instituto de Estructura Materia under supervision of Pepe Sandicharo and Salvador Montero, and in 2009 he earned his degree. After this date, he has been a postdoctoral researcher in several centers in the Instituto de Astronomía of UNAM in Mexico, in the Instituto de Ciencia de Materiales here in Madrid, then incorporated Instituto de Física Fundamental, then he went in the Centro de Astrobiología in CAB, and he followed in the Observatorio Astronómico Nacional before he finally could incorporate it again within the stabilization process. And well, now, Pablo, it will be your turn. When you're ready. Oh.
This is working in Linux. Okay, thank you. Okay, can you hear me? Fine. Okay, great. Thank you very much for attending this talk. I'm happy to be here, and I want to thank you, the IFF in general, and Alex in particular, for giving me the chance to present my work here. Okay, I am a member of the Department of Molecular Astronomy, Astrophysics, I'm sorry, and you can find me in the office C15 in the right wing of the cloister. Okay. Well, I am an astrophysicist, and I work on the evolution of solar-type stars. Okay. Okay, this is the sun. So I think we all know that well, the sun is at this moment is stable, but it will be a time in which it will not be that stable. So stars evolve due to mechanisms that happen in their nuclei, and at the beginning, its changes will be slow and mild, but in the end, it will suffer a cataclysmic event that will eject part of its matter to the interstellar medium, enriching this environment. Okay. Now the star is right now in a group of stars that can be called the main sequence, in which all the stars are stable, but eventually it will go out from this stage and will become a red giant. In this stage, it will eject matter as a wind, and in the end, it will explode in the face of protoplanetary, planetary, what is it? Oh, wait, nebula. So all this matter will travel into the interstellar medium, enriching with processed matter and with mechanical energy that could destabilize parts of clouds that are quiet and but favoring the formation of stars like this that will eventually go into the main sequence again, and so in an endless cycle. Okay. Well, I'm not going to talk about all the changes that nuclei undergone, because it's out of the scope of this talk. But we are going to consider that the star I'm going to take as example will start to grow until reaching radii of the order of 2 astronomical units, and it will start to pulsate. Okay, In this moment, we can assume that this star has entered the asymptotic Gaia branch, or AGB. These kind of stars have temperatures of the order of 2,000 to 3,500 Kelvin, and they pulsate with periods of tens to hundreds of days. One of the main characteristics of these stars is that they are surrounded by a cloud made of gas that is expanding radially with velocities of the order of tens of kilometers per second. There is a theory that can explain, currently explain what we observe, and this theory says that the mechanism of the formation of these clouds are the following one. So the star pulsates and ejects a small fraction of matter from the atmosphere to a distance from the photosphere of more or less 1 stellar radius. Sorry. And in this, it's like it's forming a kind of extended atmosphere. This atmosphere is more or less quiescent. The gas is not moving; it's levitating. And but here the temperature is low enough to allow the formation of molecules in a gas that initially was in atomic form. Okay, part of these molecules are refractory and can condense onto dust grains. Okay. These dust grains are initially small, with sizes of tens of nanometers, and the radiation of the star is able to push them away like if they were a kind of a solar sail. In this travel, these grains meets cooler and cooler gas, and more refractory molecules stick to them. Okay. And these grains grow and are accelerated by the radiation pressure of the star, and in the end, they act like a ball in a fluid and drag the surrounding gas. This is the way that in which we can move the gas from the star to outside. This process can be estimated the matter flux of this process and the mass loss rate of the star, and we can measure this quantity to have values of 10 to the minus 7 to 10 to the minus 4 solar masses per year. Okay. Regarding the materials that compose the dust grains, it depends on the chemistry of the star. An AGB star can be an oxygen-rich or a carbon-rich, depending on if the abundance of oxygen is higher than the abundance of carbon, or vice versa. So for carbon oxygen-rich stars, the material that mostly compose the dust grains are silicates and metal oxides, whereas for carbon-rich stars, they are made of amorphous carbon and silicon carbide. Okay, we can calculate the mass the ratio of the mass in form of gas and to the mass in form of dust, and we get that it is about 300 in average. So this means that the amount of matter ejected from by these stars in form of a solid state form is quite small. But even if there is not, it is not very important. They are not very important in this sense. It is significantly important for the excitation, the kinematics, the thermodynamics, and the extent of the envelope of the gas component. Okay. Regarding chemistry, the circumstellar envelopes, which are the name that we give to this surrounding cloud, are stratified. Okay, here this is the star. Here, and here the matter is in the form of atoms, mostly atoms, hydrogen, helium, and small lower abundances of heavier chemical elements, and a few simple molecules such as dicarbon, the radical cyanide, or titanium oxide, for instance. And this is this region is comprise the inner layers of the envelope, and there we can find molecules which are non-reactive and neutral. The dust grains forms here, and these grains can move these molecules, which are called parent molecules, outwards. So during the journey in the inner layers and in the intermediate region of the envelope, don't undergone important changes in their abundances, except for the case of the refractory molecules that can be removed from the gas phase. But when the parent molecules reach the outer layers of the envelope here, and they meet the galactic UV ultraviolet radiation field, which is strong enough to dissociate part of them, producing radicals that can react with other molecules. So these radicals triggers a very active chemistry based on radical and radical neutral reactions, producing myriads of new molecules. In fact, most of the molecules detected in these kind of sources have been detected in this region. Beyond this region, it is supposed that all of the molecules are fully dissociated, and we only have atoms and dust grains. So the matter that enriches the interstellar medium are actually atomic and solid state. Yeah. Well, when the stars approaches the end of the AGB phase, as I told you before, they undergone a cataclysmic event for which they eject half their mass, okay, in a big explosion or something similar. It's not an explosion from our point of view, but it's a fast process that takes only a few hundreds of years. Well, during this process, the former star is replaced by a new one that is much hotter. So the temperature of these new stars can range from 5,000 to about 30,000 Kelvin, and the stars the hottest stars of this sample, of this group of stars, are able to produce a very strong ultraviolet radiation field that will interact with the neutral recently ejected matter, producing a very complex structure that can be resumed in this way. So we have the new star in the center, surrounded by a plasma, a fully ionized plasma, which is embedded in a photodissociation region. That could be, this is more or less this. And this photodissociation region is surrounded by the remnant of the circumstellar envelope developed during the AGB phase. Okay, this is something quite complex. Well, during this phase, these stars develop collimated high-velocity bipolar outflows, like in the case of this protoplanetary nebula, which is called M29. And these outflows change completely the shape of a large scale of these stars. We can have many examples with different shapes. Most of them are bipolar, but we have different outflows and have different shapes, square or something like that. So very beautiful, everything. Well, how can we observe all this? Okay, the simplest way is using telescopes, of course, single dish telescopes like this in the picture. So these telescopes are mostly ground-based, like these telescopes here, and the IRTF. This is the Alto telescope in Spain. Telescopes in Spain. This the VLTs in Chile, and the 30-meter telescope in Granada. Okay. But part of these telescopes are launched to space, like in the case of the famous James Webb Space Telescope and the Hubble Space Telescope. And there is another class of telescopes that are in the middle. So it's a kind of hybrid telescopes like SOFIA, which are called the airborne telescopes, in which they put a telescope inside a plane. So it's very useful in some senses. Okay, but the single-dish telescopes can provide us with data easy to reduce and interpret, but they don't provide us with information about the spatial distribution of the brightness of the emission of the source that we observe. Well, it can be done for very big, very large sources, but in our case, in that study stars, it's not possible because the size of the stars are similar in size or smaller than the point spread function of the telescopes, which is of PSF, which is the size of the image of a point-like source. So we cannot get nothing from them. So we use interferometers. Interferometers works following the same principles as the Young double-slit experiment. We take two different antennas, for instance, in the millimeter range, and observe one source and make their signals to interfere, okay, producing fringes. These fringes have information about the size of the source along the direction defined by the telescopes. Okay, so if we have an array with different pairs of telescopes, we can obtain information about the size of the source along different directions. And it is possible with all this data to produce some kind of maps that could represent what we are observing. The PSF of single-dish telescopes are usually of the order of 1 to 100 arcseconds, depending on the wavelength we observe. But with interferometer, we can reach resolutions, angular resolutions of the order of 10 to the minus 6 to 10 to the minus 5 arcseconds in the case of the very long baseline interferometry in which we use telescopes located in different parts of the Earth. So in the case of ALMA, that is an interferometer that we usually use, the maximum angular resolution goes from 5 to 10 milliarcseconds. To put all this in context, we are going to say that the size of the AGB stars without the circumstellar envelope ranges from 10 to 50 milliarcseconds in the case they are close to Earth. So it's possible to use interferometers to observe even the central star. Well, the output of these instruments are complex visibilities that are entirely related to the Fourier transform of the emission distribution in the sky. So we only have to invert these visibilities to get maps of these sources. Well, with all these instruments, we can observe in different ranges of the electromagnetic spectrum. All of them are important, interesting, but I am going to focus in three of them that I think they are the more interesting, at least for me. Okay. This is the millimeter, the infrared, and the optical ranges. So, well, the excitation, molecular excitation depends on several phenomena. The first one is rotation, in which the molecule rotates as a whole. The second one is the vibration, in which the atoms of the molecule vibrates inside the molecule. And the other one is the electronic configuration, more or less, or the variations of the electronic configuration in which the electrons that make the atoms to be bounded change its configuration. So in this case, we have rotational transitions in which the molecule changes its way of rotating by emitting or absorbing a low energy photon. So one of the we have the spectrum of a molecule could be much more complex or simpler depending on the geometry of the molecule. We have a gas with different molecules with different abundances. We can have complex spectra like this one that is shown in this figure. But The rotational spectra of molecules have a very good characteristic for us, and it is that each molecule has a unique spectrum. So it is possible to use observed lines to identify molecules if we observe in the environment or the gas that we are observing in a sufficiently large spectral range. Okay, with this kind of transitions, we can observe the corresponding lines and trace um, uh, the whole envelope of AGV stars because, since they are slightly separated in terms of energy, we can detect changes involving very small, low temperatures, like in this case that we can have here, temperatures of about 50 Kelvin, for instance. The second type of transition is the infrared transition, and that is more or less the same as in the rotational case, with all the complexity of the rotational case, but we add here the movement of the atoms inside the molecule. So the spectrum is much more complex, and the photons involved in the process I usually observe in the infrared. In the other case, it was in the millimeter range. All the lines here are usually grouped in form of bands. In this case, we have a band that is observed with a low spectral resolution, and this is the reason why we cannot have information about the individual lines. But if we had it, we will see something really, really complex. This is there is some pros and cons of infrared observations with respect to the millimeter observations, and it is the following one. For instance, one of the worst things of this kind of data is that it is not possible to identify a molecule that produces a spectrum in the vibrational spectrum if we don't have enough spectral resolution, which is something that is really common, unfortunately. So this happens because all the molecules of a family vibrates more or less in the same way because they are very similar. So all the bands produced by all the molecules of this family are more or less at the same frequencies. So if we don't have a spectral resolution, we cannot study the individual lines, and it's not possible to say what molecule is producing that. But contrarily, it has some advantages. One of them is the fact that it is possible to observe the emission of molecules without a permanent dipole moment. It's something that is not possible to be done in the millimeter with rotational spectra because they don't have it. So we use this kind of spectra when we need something that can be given to us, so that rotational spectra cannot give us. And with this spectra, we can trace different, the inner and intermediate regions of the circumstellar envelopes. We can get some information about the outer region of the envelope, but in a limited way. And the last one are the electronic transitions. So they are similar to the vibrational transitions, but in this case, the upper and lower vibrational states are in different electronic states. Okay, so the spectrum here is really, really complex, and you have an example here with a low spectral resolution because it produces a lot of bands that are overlapped among them, and it is crazy. So interpret this kind of spectra is really difficult. The transitions of these transitions usually modify the configuration of the electronic configuration of the molecules by changing or moving the molecule from bonding states to anti-bonding states easily. This can have an impact on the reactivity of molecules, but we are not very interested on that point at this moment, and we are going to focus on what regions of the circumstellar envelopes we can trace with this kind of observations. And another advantage of these observations, of this spectrum, is the fact that we can observe with them diatomic homonuclear molecules, which are not available neither in the infrared nor in the millimeter range. So with these observations, with this spectra, we can trace the photosphere of the star and the inner layers of the circumstellar envelope. Again, as in the case of the infrared observations, we can get some kind of limited information about what is going on in the intermediate and outer shells of the envelope. And with all this introduction, I'm going to present a few examples to tell you what I have been doing during the last 20 years. So these are observations of one of the most important AGB stars in the sky. This is the carbon-rich star IRC 10216, or CW Leo, which is the same. And this is a sample of all the observations that we have. And this observation were taken with the 3.5 meters telescope of the Carrat Observatory and the high spectral resolution of a Carmenese spectrograph. So this is, even in this sample, which is really small compared to the total, we can see a lot of lines of the carbon. If we take all these lines and refer them to its rest frequency and arrange them, order them with respect to the energy of the lower level, we get this. Okay, here we can study the how the profiles change with energy. Here we can see how these lines present two different components. The one, this blue shifted component, which is only present in the low energy lines, and another component that is red shifted component, which is present in all the lines. With all these lines, we can do many things. Obtain, for instance, excitation temperatures for each component, and the size of the line and the central frequency of each component, to obtain information about what is happening in the envelopes. So in the case of the blue shifted component, which is narrow, the excitation temperature is of 50 Kelvin, and both the central frequencies and the width of the component are compatible with the terminal gas expansion velocity and the turbulence velocity of the gas in the outer shells of the envelope of this star. Okay. This was known since several years ago, but what I'm going to present you about the redshifted component, it is not. So in the case of the redshifted component, we derive excitation temperature of about compatible with the temperature of the star, and this temperature is the star is the only place in which we can get this temperature in this star. And this component is in absorption, so it is located between the star and us, and it is moving away from us because it is redshifted, and its width is really, really large. This means that the turbulence velocity is very, very strong. So putting everything together, we can deduce that we are witnessing some kind of matter infall on the star. There is another way of explaining all this, and could be, and it is that maybe we are watching how the star itself is shrinking during the last part of its pulsation cycle. So this is something very interesting because this is the first time that it's seen in this star. And I only seen something similar in another AGB star, so it's very difficult to get these results. Well, after that, I'm going to simplify the use of interferometry with this another star. This is a protoplanetary nebulae, one of the most important in the sky, also CRL 618. So in colors, you can see the emission of the H-alpha Barmer line mixed with atomic emission and continuum observed with the Hubble Space Telescope. So this is photometry, so we don't have information about velocities here. So, but we can get it with millimeter interferometry. So the contours in panels A, B, and C are represents the emission of the CO221 line at 1.3 millimeters, observed with ALMA. In these panels, I have plotted different velocity ranges and with different angular resolutions, and we can see how the correspondence between both images is very, very good. So we can, with this technique, assign velocities to the different structures that we are able to see with the Hubble Space Telescope. Panel C is a bit different. Here we can see very small the continuum emission of the ionized core or of this star, which is that region that was composed of plasma and was surrounded the central star. As you can see here, this star has these outflows, and this outflow to the left, east, is blue shifted, is coming toward us, whereas this one is moving away from us. Going back to panel D, I'm going to tell you that this emission is not possible to be traced in the optical, because here you don't see anything, but what we have is a very optically thick dusty torus that prevents us to observe anything behind in the optical. So, but we can do it in the millimeter range. Well, we also used observed a recombination line, H30 alpha here, and that are formed also in the ionized region. This line is not contaminated by any other emission coming from any other place of this nebula. So here I'm showing you the total flux integrated over frequency, and we can see how there is here is not. I cannot see it very well. Here it's better seen in the screen, but as you can see here, a kind of a structure that is we can define it as an incomplete ring-like structure that is inside the emitting region, and it is probably related to the stellar system that it should be inside this structure. This stellar system is thought to be a binary system, and this annular structure would be related in this case with the orbital movement of these stars. And in the lower panel, we have the average double velocity at different positions of the emitting region. And so we have here blue shifted emission, as I told you before, and red shifted emission. This is the foundations of the outflows. This is not very easy to observe. But here you can see a kind of whitish region, which corresponds to with the ring-like structure. So this is suggesting that the velocity expansion velocity field is really complex. Well, and to the right, I'm going to I want to show you the emission of the HC3N 24 to 23 line in core scale. In this place, the blue and orange contours represents the limits of the CO221 emission that I showed you before, and the black contour in the center is here represents the limits of the INA score. You can see how the emission of this line, of this molecule, sorry, comes from the neutral regions, which are here and here, and mostly from the boundaries of these regions where the UV radiation field are expected to be stronger. This is something that, well, we have other maps in which this is much better shown, but they are smaller. And this is what the chemical models predict to happen. And finally, I'm going to present one of the last works. This is ongoing, and I'm going to. I've been doing it with Alex and Pedro Carlos Gómez Calzada of the Complutense, and this is based with it. We try to find the spectrum of iron carbide. Molecules with iron are very difficult to observe to detect for any reason. We don't know exactly why. Only one molecule has been found in space to date. Has been iron cyanide. But 1 year ago, Coleman and Thuris found another 3 lines of another molecule, which is iron carbide, toward the GB star IRC 10216. As I told you, it is not clear why these molecules are not present in gas phase, but it is probably because iron-bearing molecules are very refractory, and they probably condense onto gas grains in the very moment in which can do it. We started to work, and Alex calculated high-quality potential energy surfaces for this molecule, and Pedro calculated the spectrum of this molecule around 830 wave numbers, more or less. I had observations of this star at this frequency, and we are trying to find lines here. So you can see that there are many features, weak features, that are apparently real. Most of them can be explained by reversional transitions of acetylene and hydrogen cyanide, but there are some features that cannot be explained with these molecules, and coincides with features of iron carbide. So we are not sure about this. Still, we have to explore the whole range. This is not the whole range. We have a larger spectral range, but this is promising. So maybe in the near future we can present a paper with this detection of this molecule that exists, but much closer to the star where they are expected to exist before it condenses onto gas grains. So I think it's time to finish. So thanks for the attention. I want to conclude saying that these kind of stars are very interesting, but there are a lot of work to do to understand the evolution of these stars and their impact in the galaxy. So we are going to use every instrument, spectral range, and everything to get data that could provide us with a complete view of what is happening here. So thank you.
Well, thank you, Pablo, for this very interesting talk. I don't know if there are some questions in the audience.
Just a curiosity,
yeah.
What is FDWHD? Because for me, full width have maximum, but HD, what is?
Depth.
Depth.
Yeah, exactly, because same, exactly, but since these lines are in absorption, I had to change the chronics. That's all. But it's the same. It's the width of the line, they have intensity, and it doesn't matter if it is in absorption or in emission. So it's the same.
And the second is, I suppose that when you are analyzing the spectra, the Doppler correction is already included. That's true or not?
No, actually, we with what observation? Because I presented here 3.
I have seen that sometimes you plot frequencies.
Yeah.
Apparently with no correction. Another time I have seen frequency Doppler
Yeah,
minus frequency.
So it's in the end.
What is the
Well, we use different approaches to explain this, so actually the same. So we use Doppler shifts to study the emission at different, to explain the, to correlate, better to correlate the emission, each frequency of a line with the macroscopic structure of the source. So it doesn't, there is no difference. We can work with frequencies or with velocities, but it is to find this correspondence with macroscopic reality. It's better to use velocity because it can give you information about the kinematics of the gas. Frequency is different. If you use lines at one frequency and compare with another frequency, it will change. But the velocity is the same because these features are produced by gas that is moving at a single velocity.
And the last question is, I would like to understand how you work in the following sense. You need somebody like Alex for energy surfaces. You are doing mainly dynamics?
What?
Or observation?
I do everything. So the point is, for me, in my opinion, what we have to do is dominate every single possibility of exploring a system. So it doesn't matter how you do it. What I am doing with Alex is very interesting. It is not the only way to do it, but this is a way to trying to find lines of a molecule. We can go to the lab and take frequencies, experimental frequencies, but in this case it's difficult to do it with this molecule because it's very, very refractory. So it's difficult to have this molecule in gas phase. This is the problem.
I mean, you take the experimental data from where? From the lab or from the...
I think from the lab. So, but yes, we usually take data from the lab. We produce after that the whole spectrum because most of the times it's not possible to get all the lines in the lab. So this is what Alex is doing, using experimental data to produce some spectroscopic constants, and from that produce the potential energy surfaces and improve the spectrum with theoretical information. This is welcome. No, pues no te lo ves.
So
Thank
these
you.
calculations that Alex is providing to you, do they have the frequency accuracy we need for the infrared observation?
Yes, because they are based on information taken in the rotational, in the millimeter range. So if you translate the accuracy of the lines in the millimeter range to the infrared, everything changes. In the millimeter range, this accuracy could be very, very low. But when you move to higher frequencies in velocity, it becomes acceptable.
But you need the laboratory input, no?
Yes, always. Because, well, I think trying to produce a theoretical spectrum from scratch, from first basis of a molecule, it probably is very, very, very complex. In this case, these molecules are 3 delta molecules, so it could be crazy. But I think we need some kind of constraint to get reasonably good data. Otherwise, we can get anything.
Is there more question? If not, well, let's thanks again.
Thank you very much.
Pablo. Okay, so the next speaker of the day is Álvaro Gómez León. Oh, yes, in English. Ah, sorry, some problems with languages. Okay, so he did his PhD in ECMM, yeah, in CSIC with Gloria Platero, and earned his degree in 2014. After that, he was postdoctoral researcher in the University of British Columbia, the group of Philip Stamp. He stayed there for 4 years. And in 2018, he incorporated the Instituto de Física Fundamental with a Juan de la Sierra Fellowship. And then he got finally his position here and incorporated recently.
Thank you very much.
Please,
Okay.
audience is yours.
So, thank you all for being here. I know this is a different topic for many people in the audience, so thank you for the. Because of that, I tried to do. ¿Está bien? ¿Ahora sí? Sí, se nota la diferencia. Okay, so he has this very nice paper that I recommend you all to read it, where he basically claims that the study of geometry and topology in physics started in what he calls the miraculous 30s, in the 1830s. And basically, the reason is that singularities started to be taken into account, mathematically speaking, at that time, with 3 seminal papers, okay? And because until that time, basically, singularities were weird points where functions exploded or did weird things, so nobody really focused on that. But at this time, there were 3 papers. The first one was by Airy. I don't know, probably many of you know the Airy function. So that's basically what this paper was about. And what he did was a work on supernumerary rainbows. Okay, so here you have a supernumerary rainbow. I don't know if you're familiar with it. It's when you have several copies of the original rainbow, and they have different intensity. And all this happened because 2 centuries earlier, Descartes already discovered how rainbows were formed. So this is the main mechanism. You get the light from the sun. It gets refracted and reflected in the spherical droplets, and then you get the rainbow, which is seen by the observer. And Descartes already discovered that the angle at which you would see the rainbow is 42 degrees, and so on. So this mechanism was well discovered by Descartes, and the important thing was that Descartes didn't have a formulation that accounted for these supernumerary rainbows. Okay, so he could only tell what was going to happen with one rainbow. He couldn't explain why. So after that, a few years earlier, I think it was Thomas Young, basically said that the way to reproduce the supernumerary rainbows was by using wave physics instead of ray physics. So this is basically rays of light that get reflected, and so on. But if you want to get this, you need to talk about waves, not about rays. Okay? But he couldn't give a mathematical formulation for that. And that's when Airy came in. And basically what he did was to first show that the rainbow is a type of caustic. Caustics are basically this phenomena that you see in a river when you look to the deep end of the river, and basically the light comes in, crosses a curved medium, and that allows the light rays to focus at different regions. So these are the caustics, the places where it's very, very intense. Okay, so basically the rainbow is a kind of caustic. You can see it here because they come parallel, and then they focus on some regions and defocus on some other regions. So that's why it's a caustic. And basically, in that language, these are singularities where the intensity goes to infinity. Okay, so I'm going to talk about the singularity in intensity in this case. So Airy, basically what he saw is that you can regularize these infinities by doing the wave analysis, and that's done with his famous integral. And with that, he was able to reproduce the shape of the supernumerary rainbows. Okay, and you can see how these oscillations basically are related with these several rainbows that you see there. So this was the first paper, trying to study in detail singularities. Then there was another one, which was very surprising to me when I read about it, by Wewell. And he basically studied tide dynamics. Okay? So he was interested in the dynamics of tides in different parts of the world and how they correlated. So he started doing this kind of diagrams. This is, I think, an original from his paper. And basically, you can see here a number of lines that go from 0 to 11. So these are hours of the day. Okay, so 12 hours is the period of the tides that you have. And basically, these are the maximums of the tides in the sea between England and Holland. Okay. So basically what he saw is that if you start correlating these measurements, you see a counterclockwise rotation with a node in the middle. Okay? So he's the one that started to use these cotidal lines and discovered the rotatory tidal waves, which are this rotation that you see around this point, which is called amphidromy point. Okay? These are places where the tide doesn't move at all. It's fixed at height. So in contrast to the previous case, these are phase singularities, not intensity singularities, and they have zero intensity because it doesn't move, basically. Okay, so examples of this, you can get them in physics in many different fields. So in optics, you can get an optical vortex, which is the same thing, it's a phase singularity. In superfluids, you can have a quantum vortex, or in superconductors, you can have a quantized flux. Okay, so these are all phase singularities in that sense. Here, I think it's interesting. You can see a whole map of the amphidromy points in all the oceans in the planet. And there aren't too many, and it's very interesting. This tells you all the information about how the tides move and so on. So this was the other type of singularity that he discovered was interesting and had physical effects. And the last paper of these miraculous theories was by Hamilton, the one of the Hamiltonian that we'll use in physics. Okay. And this is about singularities of polarization. Okay. So basically, he was studied what are called birefringent materials. These are materials where the refraction indices change. Okay, and basically, well, the general phenomena is seen here. You shine light into a material, and then, for example, in this case, these materials have a different index for different polarizations. So the light ray separates in two components, and if you observe from the other side, you see two rays coming out, okay, with different perpendicular polarization, for example. So he focused on these kind of materials, and in particular, he was interested in what are called biaxials, okay? So in biaxials, what happens is a very funny phenomena, because are the most complex one, all the indices are different, and In uniaxials, which are slightly simpler, only have one optical axis, you, for example, could have this phenomena that I just told you. You shine light, and it separates into rays, and you observe two at the other side. But you can insert this light along the optical axis, and they wouldn't separate. They would just go together at this particular direction of incidence of the light. Okay? But in biaxial crystals, what happens is that even if you look for this condition, they have two optical axes. What happens is that you get a hollowed cone of light, okay? It spreads the light, it doesn't go in a straight line, and it's a hollow cone, and this was observed. And for what I read, basically this is the first time that there was first a theoretical proposal of this phenomena, and then it was measured. So it was a big thing at that time. Okay, so this is basically the three papers that, according to Berry, started this field. And interestingly, during this time as well, Foucault developed his theory of his force and so on. And this is going to be related with all this because Foucault, basically at the end, can be explained in terms of a geometrical phase. And it's basically the same phenomena as I described for the other cases. And I'm going to show you all how it ties up. But this is going to be very important now to explain the planetary waves. So let me introduce it very briefly. So the Foucault pendulum is basically described by this force, okay, which is a force that you measure when you are an observer with some velocity and you are in a rotating frame. So you see that there is a force that deviates from a straight line, okay? So in general, this force is very small at our scale of the planet Earth. But there are two regimes where it can be important. So one is the long time scales, which is when the Foucault pendulum appears. Basically, you wait for a long time, and you can see the deviation in the plane of the oscillations. And the other one is when you have slow velocities and long distances. Okay, so here omega is the rotation of the Earth, basically the angular momentum of the Earth, and T is the time. Length is, in this case, for example, length scales in planetary scale, and U is the velocity of, in this case, for example, ocean or wind currents in the atmosphere. Okay. Importantly, for Foucault's idea, the Earth curvature, for the Foucault pendulum, the curvature of the Earth is very critical because it's basically what gives you a latitude dependence on the angle. But you can basically work with Newton's law, introduce this force, the tension, and so on, and rewrite everything as an harmonic oscillator with a friction, okay? And with that, you just get an analytical solution for the oscillation in the plane, the deviation due to the Coriolis force. Okay. That's what you get when you write these coordinates and so on. I mean, basically, you start with Newton's law. Oh, it means that basically it's not a dissipation, it's just a change of frequency in the plane, basically. Yeah, it's not a damping. So it's like another time scale, which is going to be slower and modulating the main oscillation. Okay. So this is the original way to get the deviation in the plane of the Foucault pendulum, but there is another way, which is very simple, and I think it's intuitive for people working in geometry and topology, and it's the following. So you don't need to know about Coriolis force or anything like that. We're just going to use something that is called parallel transport of vectors, okay? And what is called adiabatic evolution. So imagine that you have a sphere, okay? This is going to be our Earth. And you want to study the trajectory of a pendulum that is, we are going to assume, confined basically in a plane. So the height where it oscillates is very, very low. So you can just work in X and Y coordinates, let's say. And then you let the pendulum oscillate and wait for one oscillation of this pendulum. So when that happens, the Earth has rotated a little bit. So if you were initially, let's say, in this tangent plane here, now you are in another tangent plane here, which is different to the original one. So at this time, by Levi-Civita, was asked the question, how can I compare the original vector and the other vector when I have changed the tangent plane? So this is basically the problem of parallel transport of vector. And the answer is basically that to make the minimal change in the vector, what you have to do is to take a vector that has that the difference with the original one is just perpendicular to the plane. So if the difference between the two vectors is just normal to the tangent plane, that's the minimal change that you can do. Okay. So if you do that and you calculate what is the angle of rotation, you basically get Foucault's result just from a geometrical analysis where you impose that there is a curvature because of the sphere and there is an adiabatic evolution during the oscillation of the pendulum. You don't need to say anything else and you get the angle. And the reason why you get this angle in such a simple way is because it's a geometrical result. It doesn't depend on the dynamics or on many other things. It only depends on the trajectory that the pendulum has followed during the rotation of the Earth. Okay? And there are very funny ways to get the result, for example, by putting a cone with the same trajectory at the latitude that you want, and then you unfold it, and you compare the vector, the initial and the final vector, and this gives you the same angle. So there are very funny and fun geometrical ways to get this. But all I want you to understand is that you don't need to do the whole dynamics of a system to start learning about these processes. You can just do a geometrical analysis, and you will get the same result. Okay. So, for example, this result has been observed in shear waves on earthquakes. So shear waves are the ones that go with an S profile, okay, oscillate up and down, and follow the same deviation because it's a geometrical deviation, it's very general. And this is very similar as well to the quantum Berry phase, that I will go to it later on, in the sense that it's basically an angle that depends on the integral of some curvature over some path that you have followed. Okay. So how do we connect this with topology? So the way to do it is that here, for example, the angle depends on the trajectory that you followed here. So this sigma here in the integral is basically this contour that you are following in the sphere. So to go to topology, you can basically say, what happens if my volume, where I'm integrating the surface of the Earth, is a closed manifold, so it's completely closed, it's not open like a flat space, and I integrate a trajectory that covers the whole sphere. So it doesn't make sense geometrically because you're integrating everything, but when you do it, you get a number which is called the Euler number, and for the case of the sphere and the Foucault pendulum, it's just 2, 1 minus g, where g is the number of holes in your compact space. So a sphere doesn't have any holes in it. So this is the genus is 0, and you get 2. Okay? And this is basically telling you that a sphere has 2 singular points. And that's why you cannot map a sphere to a plane. So basically, the typical way to explain it is with the Hairy-Ball theorem for a sphere, that if you have a ball, a head, and you want to comb the hair, you cannot comb it all in the same direction without getting a singularity. You will get either the singularity here and the other one here. One goes away, and where they meet, all the vectors. And that's the 2 numbers. And it's basically telling you about the topological invariant of this system. Okay? Okay, so that's how I wanted to connect the introduction of topology and geometry to these different fields. And now let me move to planetary waves. Okay. So the way, so this is a friend and a collaborator of mine, and he's one of the authors of this work that I thought it was very interesting at the time. And basically what they show is that equatorial waves in our planet, in Earth, have a topological origin. These equatorial waves were known, and they were described and dynamically and physically and so on, but they basically show that it was of topological origin. Okay? So, and this is, probably you know it, very related with the phenomena of El Niño. So El Niño is a current that goes in the equator from west to east. Okay? And basically this is, I'm going to tell you, a topological mode. Okay? It gets excited at some time of the year with change in the winds, but this mode is always there, and when it gets excited, it transports heat from one part of the planet to another part of the planet. Okay? And basically, the phenomena is exactly the same as you have in a quantum Hall effect. So in a quantum Hall effect, you have a bunch of electrons, a gas of electrons with a magnetic field perpendicular to it, and that traps electrons in trajectories, and because the magnetic field breaks time reversal symmetry, you get this phase with H states that move around the corners. So in the picture of El Niño and coastal waves, what happens is that the rotation of the Earth acts like the magnetic field. It breaks time reversal symmetry in the same way. And all the waves that you have there can move in one direction. And here, these kind of waves are called Kelvin waves. And there are 2 types. The ones that go along coast. So you have a physical boundary that is solid, So the wave from the sea hits the coast and it moves along the coast, very localized. Or there is another kind, which are the equatorial ones, and they happen in the middle, and this is precisely the Niño. Okay? The other ones, the coastal ones, you can see them in lakes, you can see them in the coast, all over the globe. But the equatorial one, it happens just because the dependence on the latitude of the Coriolis force changes sign in the equator. So this change of sign is like changing the magnetic field from one orientation to the other one. So this creates a physical boundary for the modes, and they localize in the equator. Okay? And that's all you need to have them. So this is just to tell you that at planetary scales, you can have very robust topological modes that affect planetary scale phenomena. Okay? So this is just the math of how this is done. So you can do what is called a shallow water model. It's basically a model that assumes that you have a bunch of water, in this case the ocean, and the length is much larger than the height. So it's a very thin fluid. And when you do the math for this system, you can simplify things and so on. And at the end, you get to a matrix, a 3x3 matrix like this one, that you can diagonalize, and you can calculate the topological invariance in the way I shown before, just finding the genus of the sphere and so on. And you find that there are 3 topological invariants for 3 different bands that you have in the system, and they take values 2, 0, minus 2. And this is basically telling you that there will be 2 modes in the equator, and these are the modes, are called the Janai wave and the Kelvin wave. And these are localized in the equator, and it's because of this phenomena. Okay? And this has been measured with radar and so on. Okay? So this is what happens in the Earth. But in this paper, in the previous one by Pierre Delplas, what they did was to claim that it could be even more interesting in more exotic places, like in stars, because stars have very different physical mechanisms in action depending on the type of star and so on. I'm not an expert on this at all, so I'm just going to tell you what I learned. And in particular, they talk about land waves. Land waves, you can see them on Earth, because these are the ones that, for example, if you have a volcano explosion, this creates a shock wave, and the shock wave travels between the atmosphere and the crust of the Earth, and is localized and moves very fast. It can go around the Earth many times, and these are shock waves that propagate with a topological origin there. But in stars, they claim that you can have them even without a crust, without a solid mantle, let's say. And it's because in the stars you can have different regions which can be convective, can be radiative, and so on. And as the density and the processes change along the depth of the star, you could have these modes living in between. Okay? So this is the way they think this could be interesting. And well, I think it's very interesting, especially for the people working in astroseismology, which I don't know how much is related with the works that you are doing here, guys. But if you think there could be a connection or something interesting to explore, you can let me know. And I can even be in touch with the authors of these works, and we can try to think about something. Okay, so this was about the topology of stars and planets and so on. So I'm going to move now to quantum mechanics. So basically, in quantum mechanics, topology and geometry arise in the same way. You basically have vector fields with different profiles, and you can have singularities in them. And when you have singularities and you have compact manifolds, like a torus, a sphere, or whatever, you can get topological invariants that are linked to physical properties. Okay? So in quantum mechanics, we basically talk about the Berry phase, which is this one, and it takes the same form. It's just the integral of some curvature along some path, and it's a geometrical result that you cannot remove. It's a phase that you cannot remove with a gauge transformation. And then you have the Berry curvature, which has this form. And then you can calculate from this curvature topological invariants, where the most well-known is the Chern invariant. Okay, it's the one that characterizes the Hall effect physics. So historically, from this, there's been a lot of research on topological systems in quantum mechanics. And there are many invariants that you can calculate for different symmetries and so on. So this is more or less, there was a huge interest in this field when I started my PhD. And when I started basically to connect with my current research, one of the questions we asked was, is this all that is possible in this system when you have a system that has topological properties and so on? And the answer was not, because you can move to non-equilibrium systems, okay? Before, I was talking about planetary waves. This is all non-equilibrium because you have fluids moving and the Earth rotating and so on. But in the previous case, with the quantum Hall effect, it's just a gas, a bidimensional gas with a magnetic field. That's static. But then you can have systems where you also think with the different parameters in a time-dependent way, okay? So these are called Floquet systems. And basically, the Hamiltonian is periodic in time. The system is not in equilibrium because you are using energy to change the parameters externally. But it has this symmetry, which is a discrete time translation symmetry. So for this, usually, these are interesting because energy is not conserved, but the total phase over a cycle is. So this gives you quantum numbers, and you can use this theory to study the system. And basically what happens is that all the topological arguments that you have in static systems now get enhanced or enriched because these quasi-energies, which are the conserved quantities in time-periodic systems, can also wind. The intuitive way to understand it is when you have a Hamiltonian, usually it's an Hermitian operator. Hermitian operators are basically, if you diagonalize them, it's a bunch of eigenvalues. But phases are defined modulo 2 pi. So it's basically like if you take these energies and you fold them into a cylinder. So now you can have windings where the energies fold around the cylinder, around it, okay? And this gives you additional topological properties. So this is one of the fields of research where I'm working, and it gives you a lot of new results in topology. So basically, you can get new topological invariants that are not in previous systems. You get new edge modes that are time-dependent, can be propagating and counter-propagating. For example, here there is a picture of a system that could be like a quantum Hall system. And you can have edge states crossing one gap, but also this other gap. And these quasi-energies here are basically winding in the sense that I told you before. And all of this has been tested experimentally with very different experimental implementations in cold atoms, in graphene, in photonic lattice, superconducting circuits, and so on. Okay. So, in particular, I think one of the nicest setups that I know of, it's fiber ring resonators. Okay. And this is basically an optical setup where you have two fibers, which are alpha and beta, and they have a slightly different length. So you send a pulse into one of these fibers, and every time they pass this point. This is a time splitter, a beam splitter. So the pulses separate, and you start making beams with different times of the pulse crossing in the fiber, and then you can recombine them with the original pulse and see basically what is the spectrum. And you can demonstrate that these dynamics of the pulses crossing between the two rings can reproduce the time evolution of tight binding systems or even two-dimensional systems. Okay, so here is, for example, a trajectory. This is for an experiment, and this is the bands measured for a two-dimensional system using this setup. Okay, so one of the interesting things about this setup that we are trying to do now is that you can introduce quasi-periodic driving. So you can modulate this beam splitter in time, and you can do something like Fibonacci sequences and stuff like that. Or you can have nonlinear processes, because the light, as it travels on these fibers, there can be Kerr processes, so nonlinear effects in the light propagation, that basically give you higher order corrections, and you can reproduce the dynamics, for example, of Bose-Einstein condensate, so the Gross-Pitaevsky equation, and study the dynamics of these type of systems using this experimental setup. Okay. So here is just a bunch of experimental results so that you can see what is the kind of things that you get. So this is real space dynamics. This is the band structures that you measure, and this is a trivial system, and this is a topological one where you have part of the light localized at the edge, and you can see here the edge states crossing between the two bands. So here the bands are identical. The only difference is the presence of edge states because you are in a topological system. And what is even more interesting is that in this kind of setups, because these are quantum walks, the evolution is discrete in time, you can have even more enhanced topological phenomena. Okay? It's what is called extrinsic topology. If you are interested in this, I can give you a summary, but it's slightly technical, so I won't go into the details of this. So another topic where I'm working here, and it's basically started with my last postdoc here with Alejandro and with Diego. It's on driven dissipative phases. So it's about the topology of systems that are out of equilibrium, but instead of driven out of equilibrium because of a time dependence, where you change the system in time, it's because you have dissipation. Okay? So when you have dissipation, you can also use this dissipation to improve the system properties or even introduce topological features in the system. Okay? So this we do it with different mathematical techniques. One is called the single value decomposition. And you get funny things, which, for example, what is called the skin effect, which is these edge modes that are localized in the boundaries, usually in these systems become bunch. So all the modes, instead of just a pair localized, all of the modes in the system tend to localize towards the boundaries. And that allows you to get, for example, amplification of signals in different setups. So this is an interesting field that has very practical applications as well. And finally, to conclude, the other research field where I'm working is basically the natural extension of what I just told you about Floquet physics before. And it's what happens when the fields that you are using to manipulate your system in time, instead of being classical fields, are quantum fields. Okay? So when you assume that, for example, you have a material and you shine light in it, and the light produces the time dependence in the system, to control the system externally, what happens is if this light that you are shining into the system is quantum. So the difference basically is that you get back action between the two systems, and you also get entanglement, because now you are talking about quantum and quantum together, so they can get entangled. So this is a new field that is being intensively studied right now. And from my point of view, it's interesting because it allows you to link, for example, many-body topology. So you can have topological phases that light and matter are entangled, so you get many-body effects in isolated quantum systems. But it also links with non-equilibrium topology in the semi-classical regime, because if you take this light to the semi-classical limit, basically the light is the classical field that you would have in standard Floquet. And in that case, basically you should recover all the physics of the previous section. So it's a way to study the transition between many-body systems and out-of-equilibrium systems in a very neat way. And in all these systems, it have been found exotic polaritoric state, new topological states, and many-body phases that wouldn't be possible without the quantum nature of the light. Okay, and just to mention the last topic where I'm working is with a group in Zaragoza, which is on quantum computation using molecular spins. This is related with this because basically molecular spins are big spins, quantum spins, and they are trying to use them to make computations by coupling them with resonators. So the resonators are exactly the cavities that we would use in these materials, and the materials would be the molecules. So you can use the cavities to manipulate and operate quantum operations in these computers. So this is the last topic what I'm working on, and this is the summary. So if you think that any of the topics that I talked about could be interesting for your research, you want to know a bit more about it, and you just think that any of these can be useful or interesting for you in any way, just let me know. We can look at it. And yeah, thank you very much for your attention, and I'm around if you need me.
Well, thank you very much for this very nice talk. Are there questions? Oh, a lot. Yeah, so.
Look, it was a real challenge what you tried to do.
Yeah, I know. It took me some time to.
A real challenge. Okay, let me tell you. I think you succeed, but obviously you miss a lot of things.
I know. I wanted to do it very general, not go into the details at all.
Okay, very briefly. First, when you talk about caustics, probably you know catastrophe theories behind.
Yeah, exactly,
okay?
exactly.
Even the area integral by area, this polynomial is due to a catastrophe.
Yeah, exactly. It's a kind of classification of catastrophes, basically. Yeah.
Okay, so, and even more, when you reach the caustic, you risk chaotic behavior also.
You
reach chaotic behavior.
I didn't know about that.
Yeah. Okay, in our case, when you try to the dynamics of the scattering of atoms surfaces, you have corrugated surface, and when you reach the caustic, you have a chattering region. This is a signature of chaos. Okay? So I am not telling you this only because you are missing, because
No, I know.
there are a lot of things.
I know.
Okay? The second point is, maybe I am wrong, and this is something I would like to understand. If I understood well, the comparison between Foucault, Earth, and so on is you are in a sphere.
Yeah, basically singularities in manifold. That's the general idea.
But if I am right, when you use Hall, the conductivity Hall effect, you have a torus. You don't have a sphere.
Yeah,
so,
exactly.
So in a certain sense, this is something I don't understand. Why you compare a sphere with a torus?
Well, all you need to know there is that both are compact manifolds, so they're closed.
Yeah, this is true.
That's the relevant part. And now having a sphere of a torus actually gives you a slightly different result in how the singularities move and create and so on. We actually have an experimental paper that is going very, very slowly, but I hope it will come out, actually comparing what happens in a torus and in a sphere. But yeah, I mean, basically, in order to get the topological invariance, you need a compact manifold with singularities, and then depending on the details of the manifold, singularities have different topological numbers attached and so on.
You talk also about edge modes.
Yeah.
If I remember well, in the Hall effect, you have what is called skipping electrons.
Skipping orbits, yeah.
Orbits. Skipping electrons, skipping orbits.
Yeah.
This is exactly what you call a skin effect?
No, the skin effect will be in the case of non-Hermitian systems.
Ah.
Yeah. So Hall effect is, let's assume Hermitian, completely Hermitian, and in that case you get just modes crossing the gap, but it's one mode, two mode, depending on the topological invariant difference between the two bands. In the skin effect case, you get a lot of the states going localized towards one of the boundaries.
Which is the equivalence between the skipping orbits in Hall and in the Earth, in the...
Yeah, that's analogous. The El Niño phenomena, the wave that...
You observe this, the skipping orbits.
Oh, the skipping orbit will be analogous to the mode that is in the gap.
Okay.
Do you remember the plot with the... I can show it in a moment. So... Yeah, here. So these modes here, the blue and the red one, would be equivalent to the ones in the quantum Hall effect. Well, actually the red one. The blue doesn't exist in the quantum Hall effect, in the simple version of it. Yeah, so...
Okay, so first, Alvaro, let me start by congratulating you because it was seriously, it may be like the most beautiful introduction to topology that I have listened.
Yeah, the other part is too fast, I think, but you all know about my work in the group, so...
No, you really got me hooked from the beginning to the end, so congratulations.
Thank you.
And Salvador kind of spoiled the question that I was going to ask you because you compare like the integral quantum Hall effect with this phenomena of the equatorial currents that you have in a sphere.
Yeah.
But in the integral quantum Hall effect, you only have one because you are breaking.
Yeah,
the universal
exactly.
symmetry.
Yeah, so the difference mainly is that in the quantum Hall effect you have a Chern insulator on one side and you have the vacuum on the other one. In this case, because you are changing the Coriolis parameter from north latitude to south latitude, what happens is you are changing from 2 to -2, the topological invariant. So it's a topological invariant coupled to another different topological invariant.
Okay, okay. But the Yanai and the Kelvin modes
Yep.
are go in the same direction.
Yep. No, they go in the same direction.
Okay, okay. Thank you.
Yeah. It only depends on the rotation of the Earth. That's what defines the. In the same way that either a magnetic field pointing outwards or downwards tells you the direction of the Hall effect, the same effect.
Thank you.
Yeah.
Yes, well, I want to step down on the topology, but
Sure.
Remembering the bachelor, I just was learning about the Foucault pendulum. I was told, I mean, nobody needs to invoke the Coriolis force to explain the Foucault pendulum because what it was said in the bachelor is that the ideal pendulum doesn't change at all the plane of oscillation. So if you see
The idea doesn't.
oscillating always in the same plane and the Earth rotates, this will give you this feeling in Paris. So I don't know why you need to invoke the Coriolis forces.
No, in the derivation I have done by myself and copied from a book, it includes the Coriolis force, and that was gives you basically what enters in the.
To invoke that the ideal pendulum doesn't change the plane of oscillation.
I mean, all I mean is that when you do the calculation, let me see here. So you have this, the Coriolis parameter here, and it has omega, the rotation of the Earth there, and the angle theta is the latitude, so it depends on the latitude. So that is basically, this theta is the one that enters in the plane of rotation of the pendulum. It's the one that you get later on here.
So if you were a terraplanist that is something that is just plane, and you have a pendulum.
Oh, what happens, for example,
And it's rotating a plane.
if you have a cylinder rotating instead of a sphere, you don't get any angle at all. It depends on the local curvature that you have in that point.
So if I'm a terraplanist, I can
So, is there more questions? Well, if not, let's thanks
Thank
to
you.
the speaker again. And well, now it's time for a little break. So there is a coffee break prepared in the fourth floor in the terrace. So we can just all meet there. And we're back in half an hour.
Esto no sé si vale para astrofísica o no, pero vamos. No, pero es que como has tocado tantos temas.
Ya, sí.
Y lógico.